Hey, Seraphin here. Over the years, my mom and I have made many types of breads using a variety of leavening agents and methods. The simple and general straight dough method with instant yeast, the flavorful sponge and dough method with poolish, either made with fruit yeast water or a very small amount of instant yeast, the mochi-like soft and fluffy Tangzhong method, and of course the amazing sourdough or levain method. In many of our previous videos, we've shown you how easily you can make all these breads at home, giving yourselves delicious and healthy breads with an added personal touch that are fresh beyond compare. While the steps required may progress from being a relatively simple pastime to a meticulously complex undertaking, the ultimate outcomes are a stunningly wide selection of breads with different kinds of sensory attributes and, of course, different ranges of nutritional and health benefits. It's worth mentioning that many of these breads are made with only a few basic ingredients, easily available pretty much everywhere. Now, with the plethora of benefits that sourdough can literally bring to the table, it's safe to say that when it comes to bread making without using any additives, the sourdough method significantly dwarfs and outshines other methods of bread making. To add to these benefits, the complex and fascinating physicochemical and biological processes of baking sourdough bread lay out so many exciting challenges that it promises great satisfaction for those who master it. So it's understandable for many bakers to dedicate their energy and time entirely to baking sourdough bread, and in doing so, practically disregard other methods of bread making. I personally believe, though, that there are great merits in considering all the available methods of bread making, even if sourdough is your main focus. You see, while it's true that sourdough positively influences many aspects of bread quality, it doesn't mean that there's no room for improvement. To give you an idea, if you're looking for a bread recipe that's tender, moist, and naturally sweet without any additives, Tangzhong is what you're looking for. And adding Tangzhong to a sourdough recipe was exactly what we did in our previous video. The workflow was fast and simple, the bread was sensationally yummy, as you can see in the video, and here's the reasoning behind that video. Suppose we want to make a lean, soft, and naturally sweet sourdough bread. If I had to guess, the first question that comes to the minds of most seasoned sourdough bread bakers is probably, what basic ingredients do we need to add? Now, that could just be my own guess, but a quick search online confirms my intuition, because almost all the recipes that show up for a soft sourdough bread have sugar and fat, either butter, shortening, olive oil, or to a lesser extent, eggs, milk, etc. Now, what if we wanted to cut down on the fat and sugar in our bread? Or for that matter, if we simply don't want that much of them in our well-balanced diets? Say we want to eat healthier, which is a major factor that influences and drives so many people in the first place to look for sourdough bread, and hence continues to fuel the rediscovery of this intricate and highly beneficial way of bread baking that long predates modern bread baking for millennia. I guess I've digressed a little too far, but what I want to say is that adding Tangzhong to a sourdough recipe can bring us a lean, soft, and naturally sweet sourdough bread, which is something that's often overlooked because they're considered to be two completely different methods that are mutually exclusive. Here's another example of how we can improve our sourdough recipes. A few months ago, we made a video on how to make better homemade pizzas. In that video and the subsequent video on Tangzhong's percentage, we explained the justification for using Tangzhong in the recipe. One of the main reasons is to counter the loss of moisture due to prolonged baking using an electric oven. With a slight adjustment, all the relevant information in those videos is just as valid if we were to apply it to make homemade sourdough pizzas with Tangzhong. From these two examples, we can see the great potential of using Tangzhong to further improve the quality of sourdough bread, or at the very least, to address certain areas of specific demands. But you may wonder, does it make sense to put the two methods together in a recipe? Do the benefits we get merit the troubles we have to overcome? We answer these along with other questions in our previous video, and in that same video, we also showed you the pragmatic steps we took to combine the two methods to get a tasty, lean, and soft sourdough bread. In this video, we're going to take a closer look at certain characteristics of these two methods, especially the attributes that make them complement each other. We're going to try to understand the mechanism of their interactions, and hence the science behind the processes that make all the difference. Clearly, it's unfair to do a one-to-one comparison of the two methods. The simple physico-chemical processes that underlie the Tangzhong method are hardly a match for the complex and fascinating physico-chemical and biological processes that make sourdough so outstanding. But we do have lots of interesting things to talk about when they're in their roles as natural bread improvers. Before we get to that though, and to make sure we're on the same page, a refresher of the knowledge we know is probably a good place to start. So, bread making, whichever way you prefer to start after mise en place and weighing the ingredients, the first step is always to mix water and flour. And one of the most important aspects of this step is the incorporation of air into the dough. Of the air we introduce, its nitrogen content is crucial to the leavening of the dough and therefore the quality of our bread. Nitrogen is the most abundant naturally occurring gas. It makes up 78% of the air, along with oxygen, about 21%, and small amounts of other gases. When the air is trapped in the dough, the oxygen in it diffuses into the mix, but nitrogen doesn't. This nitrogen and the air trapped in the imperfections of the dough and those of the surface of our mixing bowl produce the majority of the tiny gas cells which serve as the nucleation sites into which the saturated carbon dioxide in our dough eventually diffuses into. This is of utmost importance because the yeast, or any microorganism for that matter, can't produce any bubbles from absolutely nothing. Therefore, without these tiny gas cells to start the bubbles with, most of the breads we make would be dense and flat. Additionally, this initial incorporation of air is very important because there isn't a lot of air incorporation in the following stages of bread making, such as shaping, degassing, and etc. Note, however, that even though these subsequent stages don't really mix more air into the dough, they do help redistribute nutrients to make it easier for the microorganisms to get to them. And they also subdivide pre-existing gas cells into smaller and more uniform ones. Of course, these bubbles alone do not a good bread make. You still need to have a structure to hold them in, and that sets the stage for the proteins and the starches to play their part. Now, starch accounts for about 63 to 72% of flour, 14% moisture basis, depending on the amount of proteins. The protein content can be between 7 to 15%. Cell wall polysaccharides, mostly comprised of arabinoxylans, account for about 2 to 3% of the flour. And of course, there exist other minor constituents, such as lipids, which take up about 2 to 3%, etc. We know each of these constituents absorbs water differently. Intact starch granules can absorb about half their dry weight of water, which increases up to 3 to 4-fold when damaged. So it's safe to say around 45% of the water in the dough is associated with the starch, and up to 25% with proteins, which may absorb about 1.8 times their dry weight of water. Aside from the starches and proteins, while arabinoxylans do not make up much of the flour, they can absorb up to 10 times their dry weight. So about 25% of the water stays with these polysaccharides. Water itself deserves as much credit as these ingredients. Water is a polar and hydrobonding liquid that makes for an excellent solvent. It can dissolve a wide variety of compounds, and it actually dissolves more substances than any other liquid. When we mix water and flour, water bonds and hydrates the proteins and starches. The main component of wheat proteins are gluten proteins, glutenin and gliadin. They make up 75 to 85% of the total wheat protein. A protein is a molecule made of chains of repeating amino acids. While the primary structure of a chain of amino acids is linear, it can coil and fold to form a more complex three-dimensional shape. Hydration of the proteins in flour enables the molecules of glutenin and gliadin to move about and then come together to create the unique viscoelastic properties of dough through the formation of disordered networks of gluten that we can knead into order. Now, you cannot have elasticity without continuity. That is Basic Science 101. Starch granules, being individually distinct and separate, clearly do not contribute to the elasticity of the dough. Their function at this stage is to absorb as much water as they can. They will eventually be broken down into simpler sugars by enzymes called amylases, special protein molecules that perform these functions. Meanwhile, gliadin proteins are too small to lend continuity to the dough. They're actually responsible for the dough's viscous properties. So it's left to the glutenin proteins with their high molecular weight and their entanglement with one another to provide the elasticity and strength to the dough. Further kneading realigns this initially random entanglement into a strong and continuous gluten network, and embedded in this network are the starch granules. Together they form a continuous structure that holds in the coalescing gas bubbles filled with carbon dioxide from the dough's ongoing fermentation, as we talked about before. The addition of a small percentage of salt, 1.5 to 2%, has positive effects on the gluten networks. Salt strengthens the structure of the dough. Well, technically, it interferes with both hydrogen bonds and hydrophobic interactions between the protein macromolecules. Of course, salt also plays the role of enhancing the flavor of the bread. Now, what happens if we add sourdough and tangzhong to the mix? To start with, sourdough has a major effect on starch, gluten, and arabinoxylans, while tangzhong gelatinizes the starches and practically denatures the proteins. The primary effect of organic acids produced by sourdough fermentation on gluten proteins is the increased swelling and solubility of glutenin and gliadin. This results in a softer dough with less stability and a shorter kneading time. And considering that we're also using part of the flour for tangzhong, resulting in denatured proteins, that means we are left with less protein overall in the dough. At a glance, the combination of these two methods spells nothing other than trouble for the dough. But the positive effects of sourdough and tangzhong on the starch, in a way, balance out their detrimental effects on the protein. These sourdough's organic acids cause partial acid hydrolysis of the starch, which, along with the damaged starch in the tangzhong, can exert positive effects on the starch granules, leading to an increased water uptake. Now, swollen gluten also provides more room for water uptake. So overall, we have an increase in the elasticity and softness of the dough. Another thing to pay attention to is that we always add salt to our sourdough recipes. The organic acids from sourdough and salt have opposing effects on the gluten proteins, but together they result in even greater dough strength and stability, as mentioned in our previous video on sourdough. An interesting observation we've made when adding tangzhong to a sourdough recipe is that an initial mixing of ingredients and subsequent kneading for 5 to 6 minutes, followed by a sufficient rest period of 30 minutes, is enough to get us this beautifully well-developed dough. Quite convenient, isn't it? Now, coming back to tangzhong, we know from our numerous discussions before on the subject of the tangzhong method that as we increase the amount of tangzhong we use, the gas retention, the gassing power, the proofing time, and the specific volume of the dough all suffer. But we get a naturally sweet, soft, and elastic bread that stays fresh and lasts longer thanks in part to a higher moisture content. The natural sweetness is a result of significant rises in the saccharides, the maltose and dextrin content, and the higher moisture content is due to the fact that sufficient amounts of damaged starches absorb and retain more water, and they end up producing bread with better water retention. Sourdough doesn't boost these two positive attributes in bread, at least not to that degree, but sourdough does enhance gas retention thanks to the changes in the gluten network resulting from the organic acids and our kneading, which allow for greater expansion due to softer and more extensible doughs. Given the right proportions, these two methods, sourdough and tangzhong, can really go well together. Now, let's address the elephant in the room, the giant role of a minute amount of instant yeast in our recipes. If you've been paying attention, we have not yet addressed the issues of gassing power, proofing time, and specific volume when combining these two methods. To give you a quick answer, instant yeast is the quick fix to all of this. I know adding instant yeast to a sourdough recipe could be a forbidden act for many sourdough purists, but as my long opening to this video explained, I'm more interested in exploring the many possibilities of bread baking rather than dwelling with just one method. So this is an essential step I'm making to further my cause. From this research paper on Tangzhong that we've quoted many times before, it states that the decrease in the gassing power, proofing time, and specific volume in Tangzhong bread are all most likely related to the issue of gas retention. In that case, the addition of sourdough is supposed to balance out these detrimental effects of Tangzhong, as sourdough does enhance gas retention. But unfortunately, it's not that simple. Let's start with the sourdough. My sourdough starter is usually maintained with a mature sourdough starter, fresh flour, and water in the ratio of 1:1:1. The levain is usually based on a ratio of 1:2:2, and the final dough is pretty close to a 1:5:4 ratio of levain, flour, and water respectively. As you may have noticed from my previous video on sourdough, I did a small experiment to get some real-time insights into how mixtures with these three ratios perform in my baking environment. And thanks to that experiment, I eventually devised an effective workflow, this one. This workflow gives enough time for the organisms in the sourdough to produce sufficient organic acids and consequently achieve the ideal pH drop. For many of the chemical and biological processes of sourdough to take place, the acidity range should be ideally in the vicinity of around pH 4. Besides the increased water uptake due to the swollen gluten proteins and starches that we've mentioned before, at this range, a slew of other processes take place, such as the proteolysis of gluten proteins through the endogenous enzymes of the flour, proteinases, increased solubility of arabinoxylans through acid hydrolysis and endogenous pentasinases, increased water absorption due to exopolysaccharides, and more. Each of these processes has a different effect on our dough or resulting bread. Take proteolysis. To put it simply, proteolysis is the breakdown of proteins into smaller polypeptides or amino acids, the organic compounds that make up the proteins. Proteolysis by the lactic acid bacteria of our sourdough induces softening of the dough. This can be a good or bad influence on the bread volume depending on how long we let it happen for. On the dough, unchecked proteolysis will get you this. Ugly, isn't it? So timing is really important here. Next, arabinoxylans, let's just call it AX for short. Arabinoxylans account for the majority of the small amount of pentasins we get from the cell walls of the wheat grains. Arabinoxylans can be subdivided into water extractable and water unextractable AX. We want more of the water extractable kind because the other type has a bad influence on bread quality. Sourdough acidification increases the proportion of the water extractable AX by converting the water unextractable AX through acid hydrolyzation, therefore increasing AX solubility. Endoxylanases, one of the enzymes endogenous to wheat, also cause a reduction in the water unextractable AX and increase the level of beneficial water extractable AX during fermentation. Water extractable AX have a high water binding capacity and the ability to undergo oxidative gelation during baking, so AX solubility contributes to improved softness and enhanced bread volume of the bread. Now, let's talk a little bit about exopolysaccharides, EPS, the beneficial sugar-based large polymers. They have a positive effect on the texture, mouthfeel, and taste of our bread. Some even have prebiotic effects. Prebiotics are compounds in food that induce the growth or activity of beneficial microorganisms in our gut. There are many types of EPS. Leaven, the type of EPS produced by one of the most common strains of sourdough bacteria, has been shown to have health benefits. Some strains of lactic acid bacteria can synthesize EPS from sucrose. Based on their biosynthetic pathways, EPS can be classified into homopolysaccharides and heteropolysaccharides. Homopolysaccharides are synthesized from sucrose and contain only one type of monosaccharide, either glucose or fructose. Heteropolysaccharides consist of one or several monosaccharides, and heteropolysaccharides are mostly used in dairy fermentation. Homopolysaccharides produced by sourdough microorganisms act as hydrocolloids. Their effects on the dough and bread are due to two functions. water binding, and interaction with other dough components such as proteins and starches, which is basically how they influence the structural networks during fermentation and baking. So all in all, the addition of sourdough with homopolysaccharide-producing bacteria strains can increase the softness and freshness of the crumb and improve the specific volume of the bread. Overall, physicochemical changes in the protein network resulting from sourdough fermentation enhance gas retention and allow greater expansion due to softer and more extensible doughs. In a previous video, we've talked about the thickening of gluten fibrils due to the addition of Tangzhong to the dough. The gluten in a dough with sourdough added also has greater areas of aggregated material composed of thicker protein strands. In sourdough, the presence of these thicker strands is said to account for a greater increase in loaf volume. This in turn correlates with an increased softness of the crumb and is associated with a reduced rate of staling. However, if the acidity of the sourdough is further increased, bread volume decreases. Sourdough bread cannot usually attain a level of softness like that of a Tangzhong bread. This is due to the evaporation of considerable amounts of moisture during baking, which is what we're going into next. If you take a closer look at the crumb structure of a slice of bread, or crumb grain as it's called in a lot of literature, you will see lots of exposed cells or pores. Before a dough is baked, these cells are basically the holding rooms for all the gas bubbles we mentioned before. During baking, when the dough is experiencing oven spring, enzymes work faster, the microorganisms produce their final burst of carbon dioxide, volatile organic compounds, alcohol, and water vaporize, and so on. All of these contribute to more gas. More heated gas means more expansion to these cells, and eventually the walls of these cells crack under the rising gas pressure, which triggers the exhaustion of gas into neighboring cells. The gas pressure is then subsequently contained by the external crust, which eventually results in a uniform gas pressure among all gas cells under the hardened crust. During this process, the gluten sheets are stripped into thin strands in a sheeted orientation, although they maintain contact with the starch granules at moderate temperatures, because the extensibility of the gluten sheets is not as high as that of the gelatinized starches. That is what happens to regular doughs without sourdough or Tangzhong in the oven. Unlike regular doughs, gluten fibrils are thicker for sourdough and Tangzhong breads due to swollen gluten proteins. But compared to sourdough, Tangzhong brings extra benefits, especially to the walls of the gas cells. Without Tangzhong, many starch granules stay visible on the remaining wall surface under the gluten nets. They are connected to each other at their contacted point due to the melting of starch granules under the conditions of limited water. Hence, the walls can be quite porous. With Tangzhong, the starch granules are less visible, much eluded due to their weak bond with the gluten nets, but that ends up creating a more flexible starch wall. So, in a sense, the modification of starches by way of Tangzhong improve the bread by eliminating the detrimental surface layer of starch granules and consequentially making them more useful in retaining moisture. So the combination of sourdough, Tangzhong, and instant yeast can theoretically bring us a bread with all the benefits of sourdough, enhanced to the next level with the benefits of Tangzhong, while at the same time using instant yeast to overcome their combined shortcomings. So in our previous video, armed with all this information on sourdough and the results of our investigations into Tangzhong, we set out to make a lean and soft sourdough Tangzhong bread. At first, we tried to stick to the sourdough workflow that we were so accustomed to by using Tangzhong 10. And while it turned out okay, the result was quite lacking in the sensory notes we were looking for. If you watched the video we made, you would know that we increased the Tangzhong to Tangzhong 20 and the levain to 30%. Now, you can see what we were facing by doing a quick calculation because the Tangzhong practically denatured 20% of the flour and the levain took up 15% of the flour. We were left with about 65% of fresh flour, so the dough we made was not the standard 1:5:4 ratio, but closer to the 1:2 ratio. As explained before, the new nutrients in the dough can only support 2 generations of bacterial growth, so the standard sourdough workflow that we regularly use is inapplicable here. we had to cut short the bulk fermentation time dramatically, which resulted in gassing power becoming an issue. So our solution was to add a tiny bit of instant yeast and cut the overall bulk fermentation time down to around 2 hours, and the proofing time to about 1 hour or so. So the overall fermentation time is just about half our regular sourdough fermentation time at room temperature. About 3 to 4 hours of fermentation time might seem like it's insufficient for the sourdough to develop all its beneficial effects on the bread, but if you think about it, 30% levain and half of the regular sourdough fermentation time, at that point, surely enough metabolites must have been produced by the organisms in our sourdough to kickstart the many chemical and biological processes needed for a good quality sourdough bread. So we aren't really losing that much in terms of sourdough benefits, but we are gaining tremendous Tangzhong benefits. The only problem is the gassing power. Our small experiments without instant yeast taught us a few lessons. First, the many attempts we made to extend fermentation by placing the dough in the fridge ended up giving us a very wet dough that was almost impossible to work with. Our best explanation for this is that proteolysis dealt a very negative blow to the dough. Second, cutting short on the bulk fermentation time but leaving enough proofing time for the dough, say leaving it until it doubles in size, becomes wobbly, etc. Well, sometimes this works, but the oven spring of these doughs was not as good as the ones with a small amount of instant yeast added. So at the release of our last video, we decided on the addition of a small amount of instant yeast as the best solution. If you watched the video, you would have also noticed that it is a very versatile recipe. You can even make the bread healthier by simply changing the composition of the levain by substituting whole wheat for the refined wheat flour. And that's it for this video today. Thanks for watching and bye!